Bueno, buenas tardes a todos los asistentes. Bueno, aquí tenemos unos pocos, pero online hay otros, otros más conectados. Así que, bueno, bienvenidos a esta charla, a esta conferencia del profesor Ali Samet Ongen. No sé si pronuncio bien, creo que no, perdona, de la Universidad de Dios, qué mal. Kutahya, Kutahya, bastante mal. Kutahya Dumlupinar University del Departamento de Ingeniería Geológica. Entonces, bueno, son realmente dos conferencias. La primera sobre geotermia somera y la segunda ya más, un poco más de simulación de la parte de suelos. Así que, bueno, los dejo ya. The floor is yours. Ale.
Dear Professor Natalia, and dear David, and dear Professor Assistant, and dear students, can you hear my voice? It's okay, right? Okay, perfect. Thank you. Dear Natalia, dear David, dear professors and assistants, and dear students, thank you very much for joining my presentation. First, I would like to thank to Natalia and David. When I called Natalia, she invited me here within the framework of Erasmus Plus staff mobility. So I'm going to stay here very short time, but I'm feeling like in my home, you know, you have really good university, good faculty, and what a wonderful city you have. So before the presentation, I would like to introduce myself. Natalia said something about me. I'm working as assistant professor doctor in Kutahya, Dumlupinar University in Kutahya. I'm going to show you the location of Kutahya because I'm sure that anyone knows where it is. So I'm working as assistant professor doctor. I finished my PhD in my university also. In my PhD, I worked on shallow geothermal systems. And in my master thesis, I worked on swelling soils. It's going to be our second presentation today. I'm working in my university for 11 years. So today I'm here, as I said you before, within the framework Erasmus staff mobility. So if you are ready, I would like to start to my presentation. Yes, please. And yes, as you see here, that the first presentation is going to be on a new trend on renewable energy systems, shallow geothermal energy. Maybe you have already known about it, but it's very new technology in Europe, especially in the center or the southern of the Europe is a new technology. Also, it's a new technology for the Turkey also. As I said you before, I'm working on Kutahya Dumlupinar University as an assistant professor doctor. You can see my email address below of my presentation title. So if you have any question, you can write me whenever you want. I will help you about the shallow geothermal system. I will try to answer your questions. And firstly, I would like to start to show you the location of my city. It is Kutahya, as you see here that. This is the Kutahya it's like a triangle, Istanbul, Kutahya, and Ankara. And our city is very famous with mining, for example, bore mining, copper mining, and limestone. Also geothermal sources. We are very rich for the classical geothermal system. And this is my presentation plan. I'm going to start with urban heat island effects. It's not a new term, but it's not widely known. We are going to start with the urban heat island effect, and then we are going to go to see shallow geothermal energy types. And then at the third step, we are going to talk about what's the difference between deep or classical or shallow geothermal energy, okay? And then we're going to go on with determining potential of a city or of a region. Then I'm planning to finish my presentation with heat transfer modeling It's very important and critical point for system sustainability. We are going to talk about heat transfer modeling on shallow geothermal system. We are going to see that hydraulic conductivity, flow rate, and well distance effect. Yeah, as you may know that green spaces, plants, vegetables, etc., release the rays from the sun, and it gives the hot energy to the atmosphere again. How can they do that? Via evaporation and precipitation. Okay, but if we damage to the green spaces, new building, new asphalt, new metro lines, etc., human-made infrastructures or buildings occur in our city. For example, this photo is taken from Istanbul at the same points. This is from the 1950. As you see, lots of green space occurs in this area. And also we can see the snow at the top of the mountain. You see that? This is a big mountain and there is a snow at the top of the mountain. And also this is some small island in Istanbul, in Marmara Sea. But when we focus the photo at the below of this photo, it's taken in the same points, okay? But it's taken 2 years ago in Istanbul. You see that there is almost any green spaces in here. Why this photo is like this? Because some cultural, some economic, some social factors, okay? Because the people is migrating from the village to the city center to find a job, to live in better economic conditions. So construction company is building new apartments, new buildings, commercial buildings also, some skyscraper maybe. So green spaces are destroying in Istanbul day by day. So it means that, as I said to you at the beginning of my presentation, green spaces taking sunlight and giving hot energy by using evapotranspiration, okay? But if we damage the green space, if you build new buildings, just a second, it's not working, yeah. If you build a new building, if we collapse, if we damage the green spaces, there will be loss of man-made structures, buildings, pavements, metro lines, high voltage cables, okay? So when the sunlight comes to our city, buildings, pavements, and other human-made structures is going to absorb this heat energy, okay? As a result of this situation, the city center temperature is going to be hotter than rural areas. For example, in this graph, you see that in rural area, the temperature is 30 Celsius. In the same day, in the same time, the city center temperature is higher than rural area, okay? It's very important. Why it's important, I will explain you. We called this effect as urban heat island effect. And urban heat island effect is not only effect to the weather or city temperature, air temperature, it also affects groundwater or soil temperature by heat transfer. You see that there is surface covers, buildings, subway systems, or industrial factories, industrial areas, and high voltage cables cause urban heat island effect because they are taking sunlight and they absorb the sunlight, and these areas are becoming hotter than rural areas, and then it also affects the groundwater temperature and the soil temperature. For this reason, researchers say that if we have hotter area, if we have urban heat island effect, let's use this energy as a heat source. It's low enthalpy source, but by the way, it's a heat source. And then shallow geothermal energy become a popular, especially in Europe. For example, this is an example these are my measurements in Kutahya, in my city. It's example of urban heat island effect on groundwater. Please focus on the groundwater, okay? I made a measurement, groundwater measurement in my city in, as you see here, that 42 well. I measured groundwater temperature during 2019. As you see here that in January, groundwater temperature is low, and when we close to the summer, it's going to increase, and then in the winter period, it's starting to decrease again, okay? And if you focus, this is the yearly average values. This table shows the yearly average values. If you focus location 10 and location 40, there is a big difference for the groundwater temperature, almost 7 Celsius difference, because location 40 is located in a village, in a green space, and location 10 was located in the heart of Kutahya, in the heart of city center. This is the urban heat island effect on the groundwater temperature. And also, after my measurements, I create some urban heat island map. For example, this one, the left one, for the August 2019. You see that we are making our measurement in the same aquifer. It is not different aquifer. We are making measurements in the same depth and same aquifer, okay? As you see here that this is the red one is the hottest area. And also this is the city center, building area of Kutahya city center. So when we focus to the west side of Kutahya, this is the rural space. The groundwater temperature is starting from 13 or 14 Celsius, but we come to the city center. When we focus to the city center, it's becoming hotter. Groundwater temperature is becoming hotter. There is a 3 or 4 Celsius difference between the rural and city center. It's interesting because we are making these measurements in the same day, at the same time. So it's really interesting. And also for the mark, the same map, almost the same map is, we can see the similar map for the mark months here, the right one. When we focus to the city center, we are going to see the temperature is increasing, groundwater temperature increasing. And also, as I said you before, this is the city center of Kutahya. But you may ask that, why this is hotter than the rural area? Because here is the industrial area. A lot of factories are located in here. And also, as you see here, that the temperature is higher than rural area again, okay? So we have a groundwater that has low enthalpy, okay? So we can think that we can use this low enthalpy source as an energy sources. And shallow geothermal energy has entered to the energy literature. What's shallow geothermal energy? We can separate shallow geothermal energy 2 types, closed loop and open loop. The closed loop system is based on soil and rock temperature, and the open loop system is based on groundwater temperature. What's going to be in the closed loop system? Look at here. Energy of the sun comes to the ground and warms to the ground, and cold fluid pumped out of house. There is some pipes located horizontal in front of your building. For example, there is a trench. I think it's average 2 or 3 meters. Okay, you are putting your pipes like horizontal way, or if you don't have any spaces, you can choose the vertical ways also. And cold fluid pumps out to the house, and fluid in loop absorbs the heat from the ground, from the soil, from the rock, and then loop carries heated fluid into the building, and heated fluid comes to the heat pump, and then we are increasing the heat pump, we are increasing the Celsius of fluid, and we are circulating in our home and then go inside again to the soil, okay? This is the system principle. And for the groundwater, in closed loop system, as I said you before, it's based soil or rock temperature. But in open loop system, it's based groundwater temperature, okay? We are pumping water from the 2 or 3 or up to 150 meters, 100 or 150 meters. We are pumping the water to the heat pump. And in the heat pump, you are increasing the temperature. You are heating your home, or passive cooling. In the summer, it's another option. You can make a passive cooling in summer. And then you injected your groundwater aquifer in the same aquifer also, okay? So this is the summary that I told you in my last slide. Groundwater temperature pumps the heat pump, and it's increasing and decreasing temperature in the heat pump circulator. There is always circulation in pumping, abstraction, or injecting well, okay? In the closed loop system, soil or rock-based system, soil or rock temperature goes to the thermal transfer fluid. It consists of water and antifreeze. It circulates for heating and cooling. And it is more popular than groundwater-based system because it's not taking too much time to set up your system. Also, it has less problem when we compare with the groundwater heat pump. So it's more suitable maybe for lots of space. And one of the most important things is ground source heat pumps, known as a renewable, clean, and environmentally friendly energy system. For example, in my last slide, if you focused to the roof or home, for example, here, the heat pump is working with electric. So you can produce your electricity by using solar panels. So your home is going to be all of your home, 100% renewable energy, okay? It's another option. Yes, if you ask me what's the difference between deep or classical geothermal system and shallow geothermal energy, I think the main difference is low enthalpy and high enthalpy, because shallow geothermal energy has low enthalpy, it's a low enthalpy sources, and classical geothermal energy is high enthalpy sources. When you see the graph, for example, in open loop ground source heat pump, groundwater heat pump, it's up to 150 meters, and the temperature is changing between 10 and 17 Celsius. And also for the closed loop ground source heat pump, this is the vertical one. And also, as you see, you can place your pipe in horizontal way. The temperature changes between 10 and 14 Celsius. But geothermal heat and power, for example, the hydrothermal system, direct use heat, it's very deep, you know, as you see here, that it's 1,000, maybe 2,000, maybe 800. It's deeper, and it's high enthalpy. It has high enthalpy, as I said. Okay, so the main difference is this. Also, the thermal capacities is different with shallow geothermal and deep geothermal. For example, for thermal capacities for shallow geothermal is between the 10 kilowatts to 5 kilowatts. But when we focus to deep geothermal energy, the deep geothermal system it's too much higher than the shallow geothermal system, from 1 to 50. Okay. And also the other difference is cooling. If you use ground source heat pump system or groundwater heat pump system in your home, in your building, you can make passive cooling in summer, because the soil temperature is going to be, let's say, for Kutahya, for my city, is 13 Celsius, and the room temperature is 25 Celsius. So even if you cannot operate the system, There will be passive cooling because you are going to take the soil temperature in 13 Celsius to your home, and then it's going to circulate in your home. Passive cooling, heat pump is not working, okay? And after that, you are going to inject the antifreeze fluid again to the soil. So it's a passive cooling option for shallow geothermal energy. In deep geothermal energy, it's not possible, or forced cooling for adsorption and also absorption, okay? This is another difference. In today, up to literature, we have some equations to determine theoretical or technical potential, theoretical or technical shallow geothermal potential of a city, of a region. By calculating my city, my Kutahya city, I use this calculation to calculate shallow geothermal theoretical potential. You see lots of numbers, and this is the capacity of Kutahya city center. Also, we can calculate the Madrid, Torino, for example, everywhere. You can calculate theoretical potential by using this equation. And also, there is another equation suggested by Alessandro Casasso. I worked with him in Torino for 3 months in 2019 during my PhD. He suggests this equation again, and also it's very popular, and by using his equation, we can calculate also the technical potential or theoretical potential of city of Madrid or other cities. And this is the technical potential, the way of calculating technical potential of shallow geothermal system. For groundwater heat pump system, we use this equation. Q means flow rate of water. Delta T is temperature difference of system. We always accept it 3 or 4 Celsius. And rho F and CF is specific heat water. It's specific heat of water. It's constant value. And technical potential for ground source heat pump system is this. It's suggested by Bayer. If I remember clearly, he is working in Switzerland, in Zurich. He suggests this equation to calculate the potential, shallow geothermal potential for closed loop system, soil and rock-based system. So if you use this equation, you can calculate your city potential, and you can map your city potential like me on the right side. What's the meaning of PTEC, BH, and E? It's the shallow geothermal potential for borehole heat exchanger. If you ask what is the borehole heat exchanger, borehole heat exchanger is vertical closed loop system. If you don't have any space in front of your building, you cannot replace your pipes in horizontal way. So you are going to make it in vertical way. So for the vertical closed loop potential, closed loop shallow geothermal system, you can calculate your potential by using this equation. PI means applicable borehole heat exchanger length, and gamma I is specific heat extraction rate. And this is the right picture shows that the closed loop system, ground source heat pump, shallow geothermal system potential of Kutahya city center. Yes, I think this is the most important point in my PhD. Also, for the systems, sustainability is very important. You see that ground source heat pump, shallow geothermal system has lots of advantages. But if you use this system on planet, there could be a thermal interference between thermal interactions between system. So your system is going to be fail. So if you want to apply this system, shallow geothermal system, in your home, you have to consult to professors or municipality maybe, your area is suitable or not. Because if you, let's say that you are using shallow geothermal system in your apartment, in your building, and let's say that your neighbor is also using shallow geothermal system. If they very close to each other, if the system is very close, there will be thermal interaction, and your neighbor system is going to be fail in a close future. So we have to make some simulation on some software. For example, I'm using Fecha, finite element flow modeling. Okay, I create some scenario for Kutahya city center for different times, for different hydraulic conductivity scenario, for different pumping rate scenario. I will show you my result with you. I will share. So this is the most critical and important point for this system sustainability. Yeah, this is the summary of that I talked with you, that I told you. Let's say that this city is very crowded city. I don't know where is it. I found this photo from Google Images. You see that this is dense urban area. We say that, let's think that lots of groundwater heat pump is working in this city. So it means that thermal interference or thermal interaction between extraction and injection wells or between adjacent groundwater heat pumps. So it was aimed to create thermal interaction models between groundwater heat pumps using Fecha, finite element flow software, and see hydraulic conductivity, pump flow rate, and the well distance effect. It's very important step for at the designing phase. You see the hydraulic conductivity effect scenario. It is the same points. The well distance is 50 meters. You see here that the well distance is equal for all of the scenario. Okay, but the hydraulic conductivity change depends on the scenario. For example, in here, the hydraulic conductivity is 5.1 meter per day. The second one, 10 meter per day. The third one, 25 meter per day hydraulic conductivity. And the last one, 44.42 meter per day. And when we focus the first scenario, let's say that you create abstraction and you set up abstraction and injection wells, and the distance between wells 50 meters, and you start to work, you start to heat your building, okay? And the red lines shows the ISO lines, shows the hydraulic head. So it means that your hydraulic head border reaches to the abstraction well. So it means that you are going to pump your home injected water. And the temperature is going to increase or decrease day by day. Let's say that you heat your home by using this abstraction well, and you took the temperature, let's say 16 Celsius, okay? And you will inject 13 Celsius. 16 Celsius, 13 Celsius, 16 Celsius, 13 Celsius. After that time, it's going to be, the water temperature in the abstraction well is going to be lower than 16 Celsius. Why? Because the injection well, injected water reached to the abstraction well. The reason is low hydraulic conductivity, okay? So your system is going to take 13 Celsius, 10 Celsius, let's say 10 Celsius, 7 Celsius, 7 Celsius, 4 Celsius, 4 Celsius, 1 Celsius, and system going down, okay? And the last one, again, this is a problem again, because the border of the injected water reached to the abstraction well also. And the third one, yeah, it's more safeable, more trustable. And the last one, you see that there is no problem. Everything is going very well. And I create this simulation scenario for 50 years, 5 and 0, 50 years, okay? This one was the hydraulic conductivity effect. The second effect is pump flow rate effect. If you are creating or if you are setting up groundwater heat pump to your apartment and to your building, the pump rate is another important factor. According to your groundwater, you are pumping. Let's say that you are pumping 864 cubic meter per day, and let's say 86.4 cubic meter per day. You see that the thermal interaction lines is going to very wide because you are pumping too much water. But in the second scenario, you see that the thermal interaction lines not relays very wide area. Okay, pump flow rate is another effect. Also, the distance between the well, 50 meters again. And the third scenario, this is the well distance effect. For example, at the left one, the well distance between abstraction and injection well, 100 meters. At the second one is 200 meters. You see that the ISO line of thermal interaction reached to the abstraction well. It's very fluent. You see that it's very narrow and fluent. But when we focus to the 200 meter, it's clear and there is no problem. Okay, also well distance is another important factor to design your heat pump system. So, in my last slide, I'm going to talk about the results, and the results shows that hydraulic conductivity, flow rate, and the well distance effect to the thermal zone, the wide of the thermal zone. The thermal zone boundary becomes wider and longer over time. That we expect. It's normal. While hydraulic conductivity decreases the risk of thermal breakthrough. Thermal breakthrough means system is going down, system is going to be failed. While hydraulic conductivity decreases the risk of thermal breakthrough increase. While well distance decreased the risk of thermal breakthrough increase. And while the system flow rate decreased the risk of thermal breakthrough decreased. I'm always combining both of them. And considering that the thermal interference negatively affects system performance, it can be concluded that hydraulic conductivity, flow rate, and the distance between systems should be considered in the design phase. Okay, if you want to create a perfect system, if you want to use this system long time for 50 years, 60 or 100 years, you have to take into consideration hydraulic conductivity, flow rate, and the well distance effect. Gracias, muchas gracias. And this photo is taken in front of our campus in Kutahya.